Yeah,
And Spencer's here.
I'm finally back in.
Yeah, because I didn't have the Zoom link and I found it on the old email link. You sent me a login for the computer. I'm on the iPad.
Okay, and I had to reboot my computer.
Okay. Well, anyway, we can go ahead and get the meeting started. I will officially call this meeting for LA Astronomical Society. The general meeting for May 2021 is officially called to order.
We aren't recording yet, are we?
Yes,
Yeah,
I just started recording.
Oh, okay.
Okay, fantastic. Okay, for tonight's meeting, we have of course, with the Zoom notes and everything like that. One of the announcements I will make is Spencer will send out the link for registering for the door prizes. So don't forget to register for the door prizes for tonight's meeting. That's very important. That's probably why most of you are here, besides to listen to the speaker. Okay, the first thing I would like to make a couple of announcements. First thing, Tim Thompson and I, we went over to Garvey Ranch at the end of April, and we met with the officials from Monterey Park, Robert Guerrero, and City Councilman Fred Sornoso. We gave them a tour of the facility. This was the first time in about a year since the facility was opened up. And of course, Tim and I, we had to go ahead and clear off the spider webs and all the other things associated with the going into the building. So we had a nice chat, and we gave them a tour of the facility and the observatory. And Tim and I think that they were fairly impressed with what we do. The fact that we also have the astronomy groups, the astronomy, the telescope open every Wednesday night, and the fact that we have the telescope making class over there, and we also have the Boy Scouts merit badge classes and everything at Garvey Ranch. So they were very happy with what we do with Garvey Ranch. Okay, the second announcement I would like to make is everybody has probably gotten an email. We have a scammer on the internet asking for support from LAAS. The person was Jessica Ann Smith Cornell. She is an Astronomers Without Borders board member impersonator. So if you get any contacts with, if you have any contacts from this person, please delete the email immediately. So we want to make sure we don't have any difficulties on, don't want anybody to get stuck in a scam operation from this person. Okay, we have a special thing tonight that we would like to go over. I will let John O'Brien or Kevin Gilchrist give the information on Lockwood Valley. Tim Thompson, I'll have him give a little bit of an indication of what he may have heard from Mount Wilson and Griffith Park and Garvey Ranch. And the first thing I would like to do, I would like to announce, do we have an honorary life membership nomination? I think, Spencer, we've got this set up so everybody can give a thumbs up on this nomination for honorary life membership. And that is for Robert Nolan. He basically leads the mirror grinding and telescope making operations at Garvey Ranch. He has been an active member of LA Astronomical Society since 2003. And everybody knows Bob Nolan when they go over to Garvey Ranch. They see him over there, and he's very active. He does a lot for LA Astronomical Society, for the club, and we would like to nominate him for an honorary life membership. I think, Spencer, set it up to where we have a thumbs up for everybody to give a thumbs up
Well,
or an
actually,
agreement? How's that work, Spencer, on
so
that?
actually, it's probably better if you click on the participants, and then there's a yes no button at the bottom of the participant list. Does everybody see that?
Yes.
Okay, so if you vote,
Oh,
you want yes or no.
I do not have it.
Do you have participants?
Try the reactions. If you click on reactions, that's where it is for me.
For
Well,
thumbs
where
up.
That's
React-
thumbs up. Well, there are two things. There either way you do it. I'll record it. So I have
I'll
8 yes.
just say I can't find any of that stuff here.
All right. Okay.
Then just say
And-
yes.
We'll take
I
yours
will
verbally.
say yes.
Yeah, yes for me, because I can't find it either, Jack.
Okay.
It's
so-
in the top right corner under participants. Like you
Yeah.
just click participants in your top right corner of your Zoom app and it'll be right there. And it'll give you like raise hand, yes, no, go slower, go faster.
because
Not true. I
my
don't.
I don't have it on iPad, so
All right. Well,
I'm on an
nonetheless,
iPad too, Curtis. I'm telling you, it's right
Oh.
there.
iPads are the kiss of death.
I don't see it.
okay,
I don't see anything on it. But anyway, I give approval to him.
so we have 12 yeses. 12 have voted yes, and plus about a handful of you voted verbally. 13.
Yeah, I'll vote verbally. but you didn't
Yes,
say before, I'll say
verbally
it
from
again.
Kevin, yes.
Are
Yes.
there any
yes.
no's? Are there any no's?
All
Hearing
right.
no no's, then it's unanimous then.
Okay.
I don't hear any no's. Then it sounds like unanimous. So we have then the LA Astronomical Society has granted an honorary life membership to Robert Nolan, member since 2003. And Spencer, you can go ahead. You will go ahead and alert him that we did that.
I'll
Yeah.
call him. I called him
Yeah.
and talked to him a
Spent-
couple days ago. Actually, we left messages to each other. I haven't talked to him yet.
Okay. And well, I have-
Okay. Well, anyway, just let him know that we approved his honorary life membership. Okay.
All
I
right.
will.
And I just
Okay.
reposted the link for the drawing. If so, please register for the drawing.
Okay. I'll have to find that, but I'm not
It's-
worried about that right this second.
It's in the chat.
Oh, okay. Okay,
Okay.
so I think we're okay with that. It looks like Robert Nolan, he's now an honorary life member. And then I'll go on to the committee reports. First, the Lockwood Valley Committee report. John O'Brien or Kevin, I think it's John O'Brien. You've got the floor for now.
We did have our first post-COVID dark sky night out at Lockwood Valley this past Saturday. It was not too well attended. I think there were about 13 people there altogether. Spencer can correct me if
Yeah,
I'm
that's about right.
wrong on that. Was fairly dark. There was a lot of must have been a lot of moisture in the air because Santa Clarita was really bright. There's a big light dome in that area, which I hadn't been out there for a while. I was really surprised how bright Santa Clarita has gotten. Everybody wore their masks. I was very pleased I didn't have to be the mask policeman. Everybody was cooperating, and I think everybody had a good night. It got pretty cold. I think it was 30. I left at 11. It was about 37 degrees.
It got down to 33.5, or I'm 31.5.
Wow. Of course, I drive through Bakersfield to get home. When I got to Bakersfield, it was still 70 degrees there.
Mm.
We have not decided on when we're going to restart the family nights. Family nights are a little more problematic because most of the kids aren't vaccinated yet, but we did hear today that they're opening up the vaccines to 12 and older now. So hopefully before long we can start the family nights back up again. That's all I have.
Okay. Okay, thank you, John. Next, we'll go to Ford Observatory Committee. Joe Phipps, are you there?
Didn't see Joe tonight.
Oh, Joe's not there? Okay, well, I will give an update for Ford Observatory. Joe and I were up there on Saturday night, and we had a problem with the rotating cage on the top of the telescope. And basically, we opened it up, then we abruptly closed it back up because the telescope is very difficult to use if the eyepiece cage does not rotate. We've alerted Greg Thomas about that, and he's going to see if he can get up there and figure out what's going on. He mentioned that he has never seen this problem before. So hopefully we'll be able to get Ford back up and open without too much of a problem. Other than that, Joe and I, we packed up Ford and we went over to Inspiration Point near Wrightwood there, and we were able to find Omega Centauri, which was amazing because, like John was saying, there was probably a lot of haze in the air, and we were able to actually find that. Okay, so that's what's going on at Ford. As soon as we get things fixed, we'll be able to get Ford operational again. Tim Thompson, can you give us an update from Mount Wilson and Griffith Park and Garvey Ranch, if you've got any updates for Garvey Ranch?
Well, I don't have anything from Garvey since we were there, and they haven't told me anything definitive yet. And of course, Griffith, it's practically impossible to tell what's going on there because it's a city organization, and who knows. Last time I talked to them, they said they thought they'd be closed all year, but I don't think that's going to happen now, but we'll see. As for Mount Wilson, Tom hasn't said anything to me since he talked to Daryl, and Daryl has already submitted a list of 60-inch nights. And so at some time in the near future, I'm sure they're going to open up the observatory grounds and the telescope, and we'll be able to start observing. I don't know if did he actually give you a date, Daryl? Or?
No, he did not. He was unsure. He thought it was going to be either really late July. No, not July. I'm sorry.
Late June.
Late June.
Yeah.
Maybe the last week in June we might get a date. Or July was what he thought, and that was 2 weeks ago, a week ago when I talked to him.
Yeah. And I was mistaken in thinking that the MWI board meeting was this Wednesday. It's next Wednesday, so it's still a week, after. So we'll see.
I think probably what we'll do is just require masks for everyone. I don't think that we can enforce vaccinations, although probably most people will have them that come.
Yeah.
But I think we'll probably not do food for a while until we know whether that makes a difference or not.
Yeah.
And everyone will wear masks. And I don't know, so far Tom hasn't said anything about restricting the number, but that's something that we can decide, once we have an actual first date, whether we're going to go with the full 25. I mean, the space is pretty big and the dome is open, so it's, almost outside, not quite, but if everyone's masked and we're in the dome and it's open, I think we can do 25. Maybe we'll drop it to 20. We can still make a little bit of, we can cover the night if we do 20.
Yeah.
Without a price increase.
Without a price increase, that's correct. And that is also not locked down as far as I know for this year. If it's going to be, what was it last year? 1050? What was it, John? So 1050 for a half night?
Right. That sounds right. For 60-inch?
Yeah.
1050 for a half night.
Yeah,
Yes.
I think that's right.
Okay. Yeah, but that's what I know now. I mean, it's going to open up. I think he's waiting for either the Forest Service to lift a flag warning of some sort, which they are expecting to do. So that's what we're waiting for.
Okay.
But it sounds fairly imminent, within a month or so.
Yeah. So there you have it.
And just so everyone knows that also this year I'll be doing operating as well as session directing on the 60-inch.
He's becoming a triple threat. Keep an eye on him.
Hey, Daryl, there's in the chat, there's a question about the 100-inch.
I didn't talk to him about the 100-inch, and I'm not sure if that's going to be under the same rules or not, or if they've gotten the 100-inch. If they've done work on it, sometimes they do work when it's close. So I don't know. I don't know what the status is on the 100. I'll find out though. I'll be back up there next Tuesday, not tomorrow, but the following Tuesday. I have another session with Glendale City College.
Yeah. I'm going to try and be there with you this time.
Oh, good.
Last year, didn't we? I think we reserved 100-inch night and not many people signed up for it. And my recollection is that our 100-inch nights have not attracted a lot of people. That's why we went for the 60-inch.
It didn't, and it may have been that we did have some people, but it may have gotten weathered out too.
Yeah, and the year before it was cloudy.
It hasn't been for a year, but the year before, I think maybe the 100 got weathered out, and we didn't do one even that year at all. So if it's going to open, I will gladly book a night on the 100, and I think there will probably be enough interest after 2 years of not being able to see through.
Definitely agree. Definitely agree.
Yeah.
All right. Since I find all that out, I'll let the board know, and when we can actually announce dates, then Andy will let everyone know.
Okay, thank you, Tim Thompson and Daryl Dooley for the updates on our facilities. And Tim, when you have when you attend the board meeting next week with Mount Wilson, if you could update the board of directors on what was mentioned at that particular meeting, that would be very handy to have.
Yeah.
Okay, thank you, Tim. Okay, I think it's time for us to go to our guest speaker. The guest speaker this evening is a gentleman named Rob Zellem, Dr. Rob Zellem. He's an exoplanet astronomer for NASA's JPL, Jet Propulsion Lab. Spencer, I will let you take over this. And remember, all of the members shall be muted during the time the speaker is speaking. Okay, thank you. Spencer, it's yours.
Right. Okay, Dr. Zellem. So Dr. Zellem, as Chris mentioned, he's an exoplanet astronomer at JPL and works on projects involving ground and space-based observations of the atmospheres of planets. Interesting enough, he's also the project lead for Exoplanet Watch. That's a citizen science project aided in the characterization of exoplanets. So I'm hoping we'll hear something about that as well. Dr. Zellem received a BS in astronomy at Villanova University, MSc in space science from University College in London, and PhD planetary sciences from University of Arizona. His hobbies include jazz piano, cooking, not trying to kill his plants, brewing beer, playing ice hockey, and fantasizing about retiring to work at Disney. I think a lot of us have had those fantasies as well. I know I have. Dr. Zellem, you want to take it over?
Yeah, can you guys hear me?
Yep.
Cool. And let me share my screen.
Okay, let me stop sharing. Okay, good, perfect.
Okay, and do you see the correct view? You should not be seeing presenter mode.
Right.
Cool. All right. Thank you so much, everyone, for having me. Really appreciate it. My name is Rob. I'm at JPL. Hopefully you know about JPL, everyone from the LAAS here. This picture was obviously taken hundreds of years ago, back when the LA area had water in it. It's a really cool view of lab. I really missed going to lab, although it has been nice to be working in my pajamas for the last year or so. But my building is nominally right over there, which is kind of cool to see, and a really beautiful view of the mountains here in SoCal. So yeah, as mentioned, I'm Rob. I've always been a huge fan of astronomy and Star Wars. I have, space shuttle photos of when it flew over on the 747 before it was retired. I got that photo from Tucson, Arizona, when I was a grad student at U of A. And ever since I was a little kid, I've always loved astronomy and space science, planetary science, and NASA specifically. So here's actually a young Rob meeting his hero, the spaceman, at Kennedy Space Center. And I get a question a lot is, did I ever want to be an astronaut when I was a little kid? And the answer is a hard no. I'm deathly afraid of heights. So rather than becoming an astronaut, I am what I think is the second best thing. I am what's called an exoplanetary astronomer, or an exoplanet astronomer. So let's break down this terminology just really quickly. So exoplanet, well, that's just short for extrasolar planet. Astronomers are lazy people sometimes, and long words are too much to say. So extrasolar planet, shorten it down to exoplanet. Extrasolar literally means anything beyond the solar system. I am a classics minor after all. I did not write my thesis in Shakespearean English or Latin. It was in regular English. But yeah, extrasolar, beyond the solar system, planet. Hopefully you all know what a planet is. If not, you might be in the wrong group. Otherwise, an exoplanet, therefore, is any planet outside of our own solar system. An astronomer, you probably all know what that is. That's anyone who stares at their sky, or more likely in my case, their computer for way too long. And at JPL, I'm an exoplanet astronomer, so I'm studying exoplanets, planets outside of our solar system. I'm not discovering them, but instead I'm doing is I'm helping to characterize them using both ground and space-based missions that I'll be describing about in my talk tonight. And the ultimate goal that I really hopefully will be able to achieve or help participate in achieving within my career is answering this question. And this is probably one of the biggest questions in all of humanity is, are we alone? And exoplanet astronomy, I think we're actually posed to be in a good position to potentially answer this question in the next decade or two, as we have new technology that comes online, new instrumentation, new spacecraft, new telescopes, and it's a pretty exciting time. Exoplanets is one of the youngest fields in astronomy. It's been around only since the mid-90s. And despite that, the field has come in leaps and bounds, and it's pretty cool to see it basically grow up before my eyes as I participated in it. But despite this being one of the youngest fields in astronomy, the idea of exoplanets and extraterrestrial life is something that's actually been around for a long period of time. So I'm required to show you everyone this slide. My wife is a historian. She's in the next room. So if she doesn't hear this slide out loud, she'll bust into the room and cancel the Zoom call. So let's do a little quick bit about history here. Giordano Bruno, he was that 16th century philosopher. He's actually that Emperor Palpatine looking dude on the right-hand side of your screen right there. He postulated the existence of other planets outside of our solar system. Similarly, Isaac Newton, the founder of Fig Newtons, said, and if the fixed stars are the centers of similar systems, they will all be constructed to a similar design. He actually wrote this in his book Principia, where he actually described the theory of gravity. But he's saying here in this quote that in our own solar system, we have 8 planets, 8 because Pluto's not a planet. We have 8 planets in our solar system. And whenever we go out into the night sky and we see the stars up in the sky, it stands to reason that there are planets around those stars as well. And we know today that these 2 dead guys are absolutely correct. We know of over 4,000 exoplanets to date. And we're probably going to be knowing of another 10,000 or so within the next few years. And as our technology gets better, as we know where to look, when to look, how to look, we get better and better at discovering exoplanets. And now, thanks to a lot of efforts by the community and missions such as NASA's Kepler and TESS missions, we now think there are at least as many planets as there are stars in the sky. In other words, planets are ubiquitous, they're everywhere. And where there's planets, there might also be life. So how do we answer this question? Are we alone in the universe? Well, I'll break it down to you for an easy 3-step method. First, you have to find your exoplanet. Then you have to determine if it can support life. Then 3, you have to find life on that planet. So let's take a quick look at some various ways to find exoplanets out there. Well, there's a problem. It's actually really difficult to see exoplanets. They're so far away. We typically only see the star that it's orbiting. The star is bright, the planet's relatively dim. So you either need to block out the star or use other methods to infer that the planet is there. And now we have at least these 6 methods to discover exoplanets. The 3 that I'll be focusing on tonight are very near and dear to my heart because one of them I actually did for my thesis proposal and my doctorate. Another one I'm working on a mission that directly uses it, and radial velocity method in particular is actually a very important method that we've been able to use to actually weigh exoplanets and to derive their masses. So the first method, the radial velocity method, is sometimes called the Doppler shift method or the wobble method. And what happens is that as a planet orbits around its star, the planet will gravitationally tug the star. So normally when things are in orbit around a star, the star is tugging on the planet, keeping an orbit around the star. But the planet also has its own gravity, and the planet actually induces a gravitational wobble on the host star. And that causes the star to redshift and blue shift its light. As the star comes away from us, the light is blue shifted, and as the star moves towards us, the light is blue shifted. And this gives us only motion along the line of sight, but this is very important because this gives us the mass of the planet. The bigger the planet, the bigger the wobble on its host star. So you can actually use this method directly to effectively weigh exoplanets. Another method, let's see here, is the transit method. The transit method is the method that I specialized in for my PhD. And what transits do is actually measure the change in brightness as a planet passes in front of or behind its host star. So let's pretend we're observing a star right here. If we're lucky, a planet might pass in front of that star. And when the planet passes in front of the star, it blocks out some of the star's light and causes the star to appear to dim. And the amount of light that blocks out directly tells us the size of that planet relative to its star. The bigger the planet, the bigger the dip, the smaller the planet, the smaller the dip. At best, the dip in brightness is typically on the order of about 1%. That's the size of a Jupiter-sized planet around a sun-like sized star. But this method is very powerful because it gives us the exact radius, so the size of that planet relative to its star. And as I'll talk about a little bit later on in my talk, is it allows us also to study the atmosphere of that planet itself. The transit method has historically, at least due to many different ground-based efforts and space-based efforts as well, it's been one of the most successful methods of discovering exoplanets. And 3,000 of the currently 4,000 known exoplanets were discovered by the transit method. So some good things about the transit method, some advantages is it's relatively cheap. I saw a post on the internet a few years ago. Someone used a single DSLR camera to observe a transiting exoplanet. As I'll show in a few slides, you can even use a 6-inch or even a 4-inch telescope with a relatively cheap CCD on the back to do exoplanet or a science grade exoplanet observations. Another advantage is this allows us to directly measure the planet's size. There's some biases and disadvantages though. One bias is that it's biased towards large planets in short period orbits because the bigger the planet, the bigger the dip in brightness of the star, the easier it is to see that signal. You can also have false detections such as stellar activity or eclipsing binaries can sometimes look like a transit event. And also, just like the radial velocity method, you need that special geometry so the planet passes in front of the star and blocks out the star's light. I mentioned before that 3,000 of the currently known exoplanets were discovered by the transit method. And one mission that's currently leading the charge is NASA's Transiting Exoplanet Survey satellite, or TESS. And TESS is actually an all-sky survey that is discovering new exoplanets. There's actually 4 cameras on board where it can measure a big patch of the sky at any one time. And it's now doing full sky surveys. I believe it's still in the Northern Hemisphere, if I'm not mistaken. And TESS has discovered tens, if not hundreds of exoplanets. I need to double check that exact number. But the cool thing about TESS is that TESS is expected to discover 10,000 new exoplanets. So we're currently at 4,000. We might have another 10,000 exoplanets to look at. And missions like TESS and efforts like TESS, whether they're ground-based surveys or space-based surveys, it's really important because these missions, these efforts will provide targets that we can then follow up in detail with space-based and ground-based observatories. So the Hubble Space Telescope, for example, has used the transit method to look at tens of planets and study their atmosphere in detail. The James Webb Space Telescope, which is slated to launch hopefully in the next few months, it will be using the transit method to look at tens to hundreds of planets. James Webb is giant. It's actually out here in SoCal, just outside of LAX, doing its final testing, I still believe. And that's about a 6-meter dish. That's primary mirror right there. And that big purple thing is actually its sun shield, and that's the size of a full tennis court. It's pretty giant. I was really lucky that I got to see it actually being tested out here. And it's such a massive, massive telescope that actually has to fold in on itself like origami to actually fit within the fairing of the nose cone of the rocket. And then once it's launched out into space, we'll have this really intricate unfolding process. Well, then it'll be able to finally take science observations. It's going to be really cool to watch that happen. Another mission I've been involved here at JPL is the Ariel mission. This is a dedicated mission by the European Space Agency to look at up to 1,000 transiting exoplanets. And I worked on a contribution to this mission called CASE that was selected a few years ago that will be launching with Ariel. But then even looking beyond these missions, to the 2020s, 2030s, 40s, the transit method will likely still be used by many upcoming spacecraft as well. But if you want to use the transit method to look in detail about the planet's atmosphere, effectively, you watch as the planet passes in front of the star, and the atmosphere of the planet will absorb some of the star's light. And if you observe how the planet absorbs the star's light as a function of wavelength, you can then back out the molecules in that planet's atmosphere. But you have to be watching when a transit happens. And if, for example, there's a 15-minute uncertainty on your upcoming transit, that's an extra 15 minutes of observational overhead you need to build into your observing plan, because it could come 15 minutes early, could come 15 minutes late, maybe a little bit late, maybe a little early. And this is all well and good, but if you really want to preserve and use these very precious space-based resources as efficiently as possible, you really need to know exactly when that transit will occur. You need to effectively keep things fresh. So for example, if I'm writing a proposal on the Hubble Space Telescope, I might say, okay, I want to observe an exoplanet, and that transit, I will predict it to happen at that red dashed line. However, let's say the transit time is a little uncertain, the next predicted time of when that transit event will occur. What happens if it comes a little earlier? Then I run a risk of actually partially or even completely missing that transit event. So you run the risk of actually missing completely with a world-class telescope like Hubble, like James Webb, the thing you're trying to study. And wasting time on these precious resources is actually is a big no-no, definitely. But this is actually where small telescopes can come into play. What we've been doing is we've been using the single 6-inch telescope out in Tucson, Arizona, called the Micro Observatory. And this is a robotic telescope just hanging out by, I think it's Mount Wilson or Wrightson. I think it's Mount Wrightson in Tucson, forgetting all the names in Tucson as well already. It's observing almost every single night a transiting exoplanet. And we were able to get a sample data set of observations of a transiting planet called HAP P32b. This is a hot Jupiter. It's a large Jupiter-like planet orbiting very close to its star, so it's very hot, hence the inventive name Hot Jupiter. And it's orbiting around a relatively dim star at 11.289 Vmag. And despite the telescope being only about 6 inches, despite the star being relatively dim, and also despite the tracking not being perfect, the target actually wandered across the focal plane by about 300 pixels. We're still able to get this really great looking transit with really high statistical significant observations and measurements. And we're actually able to make science-grade observations with this single 6-inch telescope. And I could say that because we actually used a bunch of microobservatory data in a paper we published last year, sort of showing the capability of small telescopes to contribute to exoplanet science. So taking this to account by looking at how well a single small telescope could do, this got us thinking, and we really wanted to launch something that was a citizen science project called Exoplanet Watch. And this is a campaign aimed at citizen scientists to routinely observe high priority transiting exoplanets. And by doing so, you can help keep these predicted transit times very fresh and efficient, so we can then more efficiently use large telescope time like Hubble or James Webb. All of our data products and our data will be immediately public to the entire community, and observers will be listed as co-authors on any published results. There's a bunch of other ancillary science cases that I won't go over tonight, but can talk about more at the Q&A afterwards. And we're right now wrapping up our beta testing right now. And we'll be hopefully launching probably next month, hopefully. So stay tuned. If you're interested in joining and helping us beta test, we're making a giant push to make everything super user-friendly and to fill in all the gaps, make sure we have all the details. Please let us know. An easy way to get in touch with us is simply to just Google NASA Exoplanet Watch. You should find our website. Our contact information is on there, as well as a link to sign up in our Slack channel, which is how we keep in touch with everyone, which is basically our forums. One of the things we've been really testing a lot and pushing a lot on Exoplanet Watch is a data reduction code called Exotic. This is our exoplanet transit interpretation code. This is originally developed by one of my summer undergraduate interns, Ethan Blazer, who's now at University of Virginia and has now since been worked on by many summer interns at JPL. And Exotic, what it does is it takes your raw FITS files, it does multi-object photometry on it, it does your aperture analysis, your sky annulus, your correct aperture size, flats, darks, biases, it plate solves, it aligns, it does everything to take your raw FITS file and produces, this is actually one of the sample plots that Exotic produces, is a sample light curve. This light curve is also fit with a Mandel and Engel light curve model, which is I'm showing you in red. And it also is actually a statistically significant fit to the data. We actually use science grade fitting routines to fit the data and provide all the necessary fits and information to then throw it directly into a published paper. So you can download Exotic here. There's the GitHub link at the bottom. You can also just find it directly linked off our website. It works actually on more than just 4 different platforms. It actually works on many, many different platforms. So odds are, if you have a telescope, you have a digital camera, you can actually start observing transiting exoplanets using Exotic. Another really cool thing that it does is it has a real-time reduction code as well. So let's say you're at a star party, right? And you want to observe a transit. Well, it just looks like a bright star. And by eye, you can't see the dim. But Exotic allows you to reduce the data in real time so that when someone passes by you, you can point to your light curve happening. You can say, hey, we're observing right now a planet passing in front of its star and casting its shadow on the Earth. So Exotic works on Windows, Mac, Linux. We're looking for people to help us sort of just iron out everything to make sure it's nice and user-friendly. And then we'll be launching next June. This being said, despite me putting so much stress on Exotic, you are more than welcome to use any data reduction code you want. If you like MaximDL, use it. If you like AIJ, go for it. If you like ExoFast, you can use whatever you want. All you have to do at the end of the day is to provide your data in a text format so you can then upload it to the AAVSO exoplanet database. We're very fortunate in that we have a working collaboration with the AAVSO to use their database to host all of our exoplanet data. So you can actually just upload your data right then and there. So you can contact me there at my email address. That's a typo, that should be 2021, hopefully next month. And eventually we'll be opening up this project to anyone and everyone, even those people who don't have their own telescopes or don't have a digital camera or live in a cloudy position on the world. We're working with some partners of ours to get free robotic data that we can then farm out and give out to people who don't have their own scopes. However, if you're an amateur astronomer, if you can do astrophotography, for example, observing transits is so much easier. You don't have to worry about so much your guiding. Your focus doesn't really matter. We just want to collect the photons. So if you can actually do astrophotography, this will be easier for you to observe than to make those really awesome photos of nebulae. All right, so that's Exoplanet Watch. I'm happy to come back and take questions about it later, but I'll get off my soapbox for now and get back to my normal talk. So another method that I use here at JPL is the direct imaging method. And as you can tell by the very inventive title, it's taking photographs of exoplanets. So this is a method that allows us actually to take a direct image of an exoplanet itself. But as I alluded to earlier, there's a big problem. It's really hard to see the planet's light through the glare of its own host star. As a thought experiment, let's take a large Jupiter-sized planet. Let's take a planet that's really, really young. It just formed. It still has a lot of residual heat from all that friction when all the gas and dust particles were colliding each other in its protoplanetary cloud. and the disk. So this planet is bright, it's big, it's hot. Well, that planet is still 1,000,000 times fainter than its own sun. It's like looking for a firefly around a lighthouse and you're observing it from the opposite side of the country. But, that's all well and good. What we want to eventually find are planets that are Earth-like, temperate planets that are small, that don't emit as much light, because we want to find life. The problem is that these Earth-like planets are 10 billion times fainter than their sun. It's like looking for one bioluminescent alga around that same lighthouse, and you're on the other side of the country. So it's a really, really tough thing to do. So how do you do this? Well, you can block out the light of the host star. So hopefully a bunch of you got to see the total eclipse that happened a few years ago. It was super cool. It was a great experience. You might remember that during the eclipse, when the moon passed in front of the sun, you could see the solar corona. You could also see stars around the sun as well. So you can imagine an instrument called a chronograph that can put a disk in front of the star and block out its light and let you see the dimmer light from the planet next to that star. And that's exactly what we do here on an instrument called the Nancy Grace Roman Space Telescope that we'll be talking about in a minute. You're basically taking a piece of hardware, you're putting it in front of that star, blocking out the star's light, and allowing you to resolve the light of the planet. And let me see if I can do this. 1 second. Share sound, optimize for video clip. There we go. I have a video that should hopefully work and explain everything about direct imaging.
A coronagraph is a way to see distant planets hidden by the glare of the star they orbit. The coronagraph reduces the light coming directly from the star to separate it from the light reflected by the planet. WFIRST doesn't block the star's light with an opaque disk as a simple coronagraph might. Instead, it uses a combination of disks with complex patterns and light-blocking stops to create destructive interference with the star's light, effectively making it disappear, while allowing the light from planets to pass through. A complicating factor is that the light picks up small distortions as it reflects off the telescope's series of mirrors, and these distortions can reduce the effectiveness of the destructive interference. Collecting more light increases the image signal, but the planets are still hidden under blobs of leftover, distorted starlight. To remove these blobs, the coronagraph has special deformable mirrors that can change shape by using hundreds of tiny pistons. This corrects the distortions in the light beam. As the mirrors deform, the blobs of light slowly begin to disappear, revealing brighter planets. Further adjustment brings fainter planets into view. Advanced software processes this data, further improving the contrast and clarity of the image. This processing makes objects more than 1 billion times fainter than the star visible. As a result, WFIRST will provide the first look at individual planets in star systems that might be similar
So
to
we'll
our
be
own.
returning to this mission a little bit later on in my talk, but hopefully everyone's a pro now at direct imaging. There'll be a quiz later. I'm kidding. But basically direct imaging works by using hardware and also really advanced software as well to remove or null out the light of the host star, allowing you to resolve the very, very small, by comparison, light emitted or reflected by the planets themselves. And the direct imaging method has actually been used very successfully from ground-based telescopes. So here actually is an animation of an extrasolar system. And this is called, I think this is HR 8799. And what you're actually observing over 7 years is the light of 1, 2, 3, and 4 exoplanets actually orbiting around its own star. And you can actually watch the planets orbit around their star in real time over the course of the 7 years. So effectively, we're now observing extrasolar solar systems, which is absolutely mind-blowing. It's a really impressive animation here. Okay, so now what? We have discovered now over about 4,000 exoplanets, but so what? We've discovered tons of exoplanets. We know that they're everywhere, that on average, there's at least one planet for every star in the sky. But now how do we take that next step? How do we go from where we are, which is exoplanet discovery, to now start going on to the next phase, to planet characterization. How do we, for example, determine if a planet has an atmosphere? If that planet does have an atmosphere, what molecules are present in its atmosphere? Does it have water? Does it have methane? Could it have the right combination of molecules in the atmosphere where that planet could support life? But just because it could support life doesn't guarantee that a planet does have life. So one of the last questions, one of the hardest to answer, is, does that planet have life on its surface? Which brings us to the second step, determining if a planet can support life. So how do we do this? How do we find planets that are likely to be habitable, have habitable conditions on their surfaces? Well, one of the main tracers that we use is something called the habitable zone, also sometimes called the Goldilocks zone. And this is the zone where liquid water can exist on a planet's surface. And it's important because it requires liquid water to survive. So if we look at this image here, you can see the sun, the Mercury and Venus, they're a little bit too close to the sun. They're a little bit too hot, can't support life, no water on their surface. Mars is a little bit too far away, a little bit too cold, no liquid water on its surface. Earth is just at the right distance from the sun. It's not too close, not too hot, not too far away, not too cold. It's in that nice temperate band where water can survive on its surface. And that's why people got so excited with the announcement of the TRAPPIST-1 planetary system discovery, because these were 7 Earth-sized planets orbiting around a very small star, and 3 of them, E, F, and G, might be in the habitable zone of their host star. In other words, we might have already discovered a planet or a system of planets that might have the conditions to support life and actually might have life on their surface today, which is pretty incredible. So that's how we can whittle down the entire 4,000 planet long list of known exoplanets. We can say, okay, we know that life requires liquid water to survive on the surface of the Earth. So if we want to find Earth-like planets, we have to find planets in the habitable zone. So that really narrows it down. But then how do we make the next step? How do we figure out what molecules are in the atmosphere of that planet, or even if the planets have an atmosphere at all? And to do this, we actually use something called Beer's Law. So here's a really good overview of really what Beer's Law is. It's studying for a test or doing homework while Beer is involved, making difficult classes such as physical chemistry more bearable. That's a good Beer's Law. I definitely studied that a lot as a graduate student, but the real Beer's Law is this. And essentially what it does is it describes the absorption and scattering of light out of a beam. In other words, if we have a chamber full of gas and we put a light bulb on one side, and then we observe that light bulb on the other side, that light bulb will be a little bit dimmer because the light from the light bulb is absorbed and scattered by the chamber of gas itself. In other words, and then we can actually use an equation from Beer's Law to describe that attenuation of light. And if we know what the light should have been, and compare the light to what we actually observe it as, we can then mathematically calculate what the gases are. Sorry, I'm getting distracted by the chat. That's awesome. You're sitting next to Goody and Young Tim. We can actually determine what molecule is in that gas chamber. Another way we can also think about this as an astronomy exercise, right? If we're observing the light from a yellow star, that yellow star would give off yellow light. And we say it's a yellow star. But if we put in between us and that yellow star gas cloud, right? That cloud of gas and dust will absorb some of that yellow light and make the star look redder than it should be. So if we can observe what the object does look like and compare that to what the object should look like, a yellow star, we can then use Beer's Law to determine the composition of the absorber. So we can determine that cloud has molecules in its atmosphere. So just by looking at how the light is attenuated by this absorbing medium, we can actually figure out what molecules are present in that medium as well, which is pretty incredible and helpful because the nearest planetary system to us is over 3 light years away, quite a bit of a distance to travel. Another way we can use Beer's Law is also study exoplanets. So let's take a really young exoplanet, still has that really hot molten core that's giving off a lot of heat. As that core radiates heat outward, it radiates through thicker parts of its atmosphere that are comparatively cooler than the warm core. So what light was originally radiated as yellow might look red to us, and astronomers at the other end of those telescopes can say, hey, that exoplanet has methane on its surface. You can also use this to study reflections. For example, in our own solar system, the sun will reflect or emit yellow light, which then will bounce off the surface of Jupiter, and then Jupiter's clouds will then reflect it back to us. And astronomers looking at that reflectance spectrum by using Beer's law can say, hey, that planet has clouds on its atmosphere. So Beer's law, again, allows us to characterize an exoplanet's composition by observing how it emits, absorbs, and reflects light. Again, just by looking at the light, we can figure out the composition of these objects. So to really bring home spectroscopy, this is taking the light absorbed, emitted, or reflected by an object and stretching it out into all the wavelengths that make up that light. So on this axis, we have various exoplanets that are plotted out. On this axis, right here, this goes from cool at the bottom to relatively warm at the top. On this axis, we have various wavelengths from 1 to 2.6 microns, just a little bit more red than our eyes can see. And you'll notice all these bumps and wiggles in the spectra of these exoplanets. And these all correspond to bumps and wiggles that are due to absorptions by various infrared absorbers, particularly molecules. So for example, if you see a bump and wiggle at these wavelengths, you can infer that that planet has water in its atmosphere. You see a bump and wiggle at these wavelengths, this is where methane most strongly emits. You can then assume that that planet, or hypothesize that that planet has methane in its atmosphere. And this wavelength right here is where carbon monoxide most strongly absorbs light. So some of you eagle-eye observers might have noticed these lovely gaps in the data. Well, I forgot to say that all this data was actually taken by ground-based telescopes. And as you guessed it, this is where the Earth's own atmosphere gets in the way. So unfortunately, there's lots of annoying things in the Earth's atmosphere, like water, like oxygen, carbon dioxide, all that annoying stuff really gets in the way. These are actually 3 strong telluric or Earth water absorption bands. So if you can't observe at these wavelengths because the Earth's own atmosphere is blocking it out, what do you got to do? Got to go up into space. And this is why the Hubble Space Telescope, James Webb, and other future telescopes are so very important. They allow us to go above the Earth's atmosphere to get outside of that absorption bands, and allows us to then directly observe wavelengths that we then otherwise normally couldn't observe from the ground. The Hubble Space Telescope, for example, has this instrument called WIF-C3, or the Wide Field Camera 3, that operates at these wavelengths right here, which are very strongly attuned with water absorption. So a reason why you might be hearing so many news stories about why Hubble has or has not found water on exoplanets is simply because we're biased by our own observations, by our own instrumentation. One of the instruments that we typically use is WIF-C3 and Hubble, and the wavelengths of WIF-C3 line up with molecular water absorption. So that's why we're mostly looking for that. But that's why we're excited looking forward to the launch of James Webb, because James Webb will have a larger primary mirror, higher signal to noise, higher precision measurements, but also James Webb will have a larger wavelength range access. So it'll open the door to us being able to observe at many, many different wavelengths to look for things like methane, carbon dioxide, other molecules that you can put together and potentially infer that life exists on the surface of these planets. Another mission that I'm working on here at JPL, as I mentioned before, is the Roman Space Telescope. This is formerly WFIRST. This was named in honor of Nancy Grace Roman herself. She's actually sometimes called the mother of Hubble. She was actually the first chief astronomer of NASA back when it formed. And she was one of the key voices in support of launching the Hubble Space Telescope. And in her honor, NASA named Roman after her. And this is a cool telescope because it's actually the same size primary mirror as Hubble, but has 100 times the field of view. So it actually can observe a lot larger chunk of the sky at any given time. One of the instruments on board is called the Chronograph Instrument, or CGI. And this will be using direct imaging to observe exoplanets. And this will be launching in the next 5 or 6 years or so. So what makes Roman and the chronograph so special is that it's really being that very necessary stepping stone from where we are to where we want to be. Currently, direct imaging is typically done with large 8-meter class telescopes or larger, sometimes even some 5-meter telescopes like Palomar, for example. And with these large observatories, we're typically only able to see really young planets that still have a lot of residual heat, that are emitting a lot of light, but that are also far, far away from their host star, like 50 to 100 AUs of far, if not farther away than that. However, what we really want to get to eventually is observing small Earth-like planets that are small, that are cool, that are dim, that are close to their star. So how do you go from where we are to where we want to be? And the answer is with Roman, because Roman is a technology demonstration. It's called a tech demo mission. And what it will do is it'll demonstrate all of these direct imaging technologies, the hardware, the software in space, to push that boundary a little bit closer, to look at planets that are a little bit dimmer, a little bit cooler, that are a little bit closer to their stars. So we'll be able to actually, for the first time, look at true Jupiter analogs, planets that are exactly like Jupiter, except outside of our solar system. And Roman will provide that necessary stepping stone from where we are currently to where we want to be with future missions, missions that come after Roman, that will be doing direct imaging observations of Earth-like planets that might be habitable. So it's a very necessary tech demo, the lessons learned from which we'll be using for future space missions. So someone might be saying to yourselves out there that why even bother with the ground? Well, space-based telescopes, you're not limited by Earth absorption and you're minimally impacted by sunlight. However, the resources available in space are very, very few and precious. They're very limited, therefore, in available time and also wavelength space. Typically, when you launch a spacecraft, it's very hard to add new instrumentation or to swap a camera on. Whereas, here on the ground, you can just pull off your DSLR and throw back on your 2-inch eyepiece pretty easily and do some optical observing. So that's where the pro is from ground-based telescopes. There's numerous platforms and instrumentation available, but there's the cons is that you have to look at the Earth's atmosphere. And also you have typically more sources of error that can dominate over your observations. They're sometimes less stable than space-based observations. One such instrument I've been working on here at JPL is something called NESSI. This is the New Mexico Exoplanet Spectroscopic Survey instrument. And NESSI is actually located here at the 200-inch Hale telescope at Palomar Observatory. Really lucky to have such a world-class observatory within driving distance from me out here in the San Gabriel Valley in SoCal. And it's pretty incredible that this telescope, which was commissioned in 1948, I believe, this actually was never built for exoplanet science at all. And just thanks to our instrument being effectively slapped onto this telescope, now 70 years later, we're able to actually add in this new science case to this telescope, which is pretty incredible and really honoring. It's a huge honor to be able to use such a historic telescope as well. This is the world's largest telescope for about 50 years or so. So that's a cool sort of bird's eye view of the entire observatory and site out there. I really miss going out to Palomar. Hopefully I'll be able to do that soon. And here's a picture of the instrument itself. This is a picture of Nessie. No, that's a mythical sea creature. Sorry, everyone. Here's a real picture of Nessie. This is Nessie in the electronics lab, or the E-lab, if you've ever been to Palomar. There's the Nessie doer right there, handling cart. Here's some of its hardware. I think I'm doing some flat field tests, and there's a big, nice tank of liquid nitrogen in the back to keep it cool. Here's a picture of Nessie for its first lift check that was done, and fit check that was done a few years ago. This is the principal investigator of the instrument. This is Michelle Creech Ekman. She has a PhD and also the PI of the instrument. She's a New Mexico tech, and I love her t-shirt here. It's I Want to Believe, with a picture of Nessie on it. There's my boss, Mark, ignoring me like usual to get a nice photo. And Nessie sits at what's called the prime focus of the telescope. So normally when you think of a telescope, you have light come in, hit the primary mirror, hit the secondary mirror, then it goes through a hole in the primary to where your focus is, where your instruments are. Nessie, however, in order to preserve its large field of view, we actually mount it at the top of the telescope and flip out the secondary mirror. So to do that, we have to hoist Nessie from the ground floor of the observatory over this very historic 70-year-old primary mirror and put it on top of the telescope. So here's the photos from that first ever lift test. Right about now, we're praying that our insurance is started because we don't want to wreck Palomar at all. But needless to say, Nessie did actually successfully make it to the top of the telescope. And here's Mark smiling because everything fits, the computer's on, everything seems to be working. Mark actually isn't smiling, he's actually laughing at me because if you remember, I'm deathly afraid of heights. But I am the JPL commissioning lead at Palomar Observatory. So I have the honor of going to the top 10 stories up in the air to work on this instrument. That's fun. But I got a really cool photo of Nessie, kind of a selfie. There's my feet there, and it looks like a spacecraft. So I thought it was pretty cool. And in the limited observations we had with Nessie and Palomar, we're finding that we're able to make very high precision measurements of transiting exoplanets. So that's somehow the various ways we can actually use instrumentation to then follow up exoplanets that have been discovered. We can use Beer's law to look at the atmospheres of these planets to figure out what constituents are in those planets' atmospheres, and then we can determine if that planet might have the right conditions that could support life. But just because a planet could support life doesn't mean it does have life. You have to make that next step. You actually have to find life on its surface. So how do we do this? Well, we can launch a mission, and as it's soaring out to the rest of the solar system, we can have it point back at Earth, and we can take spectra, we can take images of the Earth itself, and we can analyze the light reflected and from the Earth itself to sort of figure out, all right, what bumps and wiggles in the spectrum of the Earth correspond to biological life? Well, you can look for evidence of oxygen, ozone's produced by algae. You can look for that. You can look for liquid water, such as in Earth's oceans, or you can also look for signs of biological activity like cow farts, right? You can look for signs like methane to determine that that planet has life. The problem is you have to rule out all other explanations, because a lot of these molecular compounds can be formed abiotically without life. So taking that last step is actually one of the hardest, is how do you prove without a shred of doubt that a planet does have life on its surface? And that's what a lot of people are spending a lot of energy on doing, looking for trying to determine the biosignatures or the spectra bumps and wiggles that definitively determine if a planet does have life on its surface or not. You can also go about it in a completely different way. You can, for example, send messages to aliens. Voyager 1 and 2, they were built here at JPL. They were launched in 1977. They did a grand tour of the solar system. They had these golden records on board that were created by a committee chaired by Carl Sagan. And these are the golden records, they're phonograph records, and they have recordings of many people saying greetings in various languages across the Earth. They also have photos of Earth scenes as well. And the cover of the record's pretty cool in particular because right here, this teaches people, or aliens really, how to make the phonograph to read the record. This tells them, I think, about this is molecular hydrogen and its energy decay, if I remember that correctly, and how to read off the information from the record correctly. This is how to project the image on your TV screen, I guess, your alien TV screen. And right here, this is the location of the Earth relative to a bunch of pulsars. So this allows aliens to actually figure out where the record came from. Another way is you can send messages such as SETI has done in the past. Frank Drake and Carl Sagan, for example, actually wrote a message to two aliens in the 70s using Arecibo, RAP. This is one of the world's largest radio telescopes. And they actually sent this message on the right to the globular cluster M13. So here you can probably figure out what this is. That's a person. Up here in white is demonstrating we know how to count. This is about molecules and atoms. This double helix feature is DNA. This is our solar system. There's the sun, Mercury, Venus, Earth elevated, because that's where we live. Mars, Jupiter, Saturn, Uranus, Neptune. And guys, this was in the 70s when they didn't know any better. They thought Pluto was a planet. Well, we know better than that today. Pluto is not a planet. It shouldn't be there anymore. And down here is actually a top-down view of Arecibo, the radio dish. So this is saying, hey guys, we're humans. We think we're kind of smart. We want to count. We know about molecules. We know about DNA. We sent this message using radio waves. Here's where we live. Come and take us over, please. So who knows? Maybe aliens will get that one day. So the question is really is, where are we now? You know, unfortunately, despite what some TV shows might tell you, we have yet to make any conclusive detection of extraterrestrial life. And the question is, why haven't we? If there's as many planets as there are stars in the sky, one could say that life should also potentially be very common, right? So why haven't we found aliens yet? Well, maybe it's because our technology isn't good enough. It wasn't until the mid-90s that we actually discovered the first exoplanet. And some of the new technology that's come on are digital cameras, for example, that allow us to be able to take higher precision measurements, to do a better job on data reduction, to uncover that very small planetary signal. Alternatively, maybe we just haven't found them yet. Maybe they've been talking to us from over here. We've only been looking at this patch in the sky. The universe is really vast. Jill Tarter, who is the SETI scientist who was the inspiration for Carl Sagan's book and movie Contact, she gave a great analogy. If you were to take the entire universe and shrink it down into the size of the Earth's oceans, despite all we know, and despite how much discovery and understanding we have about the universe, we've still only about explored the equivalent of one glass of water. So there still is a ton out there for us to still explore, discover, and understand. Or maybe most depressingly is maybe we are all alone. Maybe life truly is this very unique, special thing, and maybe it only happens here on Earth. Personally, I am more optimistic than that. I think that life is likely somewhere out there, and it's just only a matter of time until we discover it. And really, that could be happening within the next decade or so. If we look at exoplanet missions and exoplanet efforts, we have this really great foundation that's been provided to us by ground-based telescopes. And then also some space-based telescopes, such as the Hubble Space Telescope, Spitzer, which was retired about a year and a half ago, Kepler and TESS, which have discovered hundreds, if not thousands, of exoplanets. The James Webb Space Telescope will be the successor to Hubble. It's a much larger instrument and it has a higher precision. And James Webb will be doing outstanding science on exoplanet discoveries. The Nancy Grace Roman mission to demonstrate that you can use these deformable mirrors to do direct imaging actually in space. The Ariel mission by ESA, as well as other European Space Agency missions to discover new transiting exoplanets. But I also want to call your attention to these three missions down here. Right now, there are astronomers that just finished up meeting to sort of determine where our field will be going the next 10 years. They do this every single 10 years. This is called the Decadal Review. And they're basically going to be writing a report suggesting where NASA should be spending its money on what sort of direction it should be going on for missions. And there are 4 flagship missions under consideration for the Astro 2020 Decadal Survey. 3 of them are called LUVOIR, HABEX, and the Origins Space Telescope, or OST. And all three of these missions have been explicitly designed to discover life on these transiting or directly imaged exoplanets. So if any 3 of these missions are selected, which are slated to launch hopefully in the 2030s, we might be able to finally answer that age-old question that's been encapsulating us for all these years and answer finally, are we alone? And with that, I just want to thank everyone so much for their attention and for having me, and I'm happy to take any questions.
Fantastic presentation, Dr. Rob. I've seen 5. Are you able to hear me? No? Oh, great. Okay, I was able to. I've seen like 5 exoplanet lectures so far, and yours is really one of the best I've heard and seen. And your presentation is fantastic. I'm just curious if you have. Are you familiar with Dr. Frank Marchese at SETI?
Yeah, so Frank actually, I love his scopes. They're amazing. It's incredible all the transit observations that you've been able to get with those relatively small telescopes. That they're 4 inches, right?
Yeah, 4.5. We have the unistellar EV scopes are what we are using. Yes, for the exoplanets.
Yeah, so Frank actually has been starting to upload some of the observations to the AVSO database. I think some of them actually might already be on our website on our results page as well. So we're trying to run our database, our pipeline, at least once a week, if not every night. And we're getting closer and closer to doing that. But yeah, seeing the unistellar EV scopes is incredible. It's awesome. It really shows the power of what you can do with a small telescope for sure.
Yeah, thank you. And we're having fun with them.
Oh yeah, they're really cool.
Again, thank you so much for doing this presentation. Everybody's muted. Go ahead and talk, guys. So unmute yourselves.
Yeah, old Jack out here in the high country of Colorado. And I just want to say, excellent presentation. Thoroughly and completely enjoyed it.
Thank you. Appreciate it. Yeah, and just to reiterate, any of you who do astrophotography can definitely do transiting exoplanets. We have a bunch of users on our Slack channel, for example, that post these beautiful photos of nebulae and planets and galaxies. And it blows me away because I just can't do it. I tried astrophotography. I'm horrible at it. And then when they do these observations of transits, they say back to me, Rob, I can't believe I'm observing a planet. And it's like, guys, your astrophotography images are so amazing. And I'm just impressed by those all the time. You know, your focus doesn't have to be perfect. Your tracking doesn't have to be perfect. We predict that you can even use 4-inch telescopes. And as the EV scopes are showing, 4.5-inch scopes can do transiting exoplanet observations. So if this is something that you're interested in helping out, please go search for our website on Google, send us an email. There's a link to be hooked up with our Slack channel. Or alternatively, if you want to wait for our launch in a month or so, stay tuned as well. We'd love to have your participation in that.
Great.
So I have a question. When you're collecting all this information from all these small telescopes, obviously the transit period could be quite long, and maybe longer than one observing session. So are you putting that all together? Or?
Yeah, so actually we are collaborating with as well the Exo Watch group out in the UK. They're, Exo Clock group out in the UK. And we have plans on eventually adding support where you could actually start a transit, for example, that happens in Europe and finishes up in the US, and you can combine those observations together. You could similarly do that across the US. So for example, if a transit starts up in the East Coast, but the target sets on the horizon, you could pick it up on the West Coast and combine all your observations together.
Being afraid of heights, I have to commend you on going up 10 stories on that Palomar, and that's huge. I don't know how you do it.
I don't know either. It's worth it. It's really a huge honor to use such a historic telescope, and I'm really lucky that I can drive there in about 2 to 3 hours and use it. I really miss it. I haven't been there in a year and March. Yeah, a year and almost a month or two ago, and hopefully we'll be going out at the end of this month to do some engineering work now that we're all starting to get vaccinated, which is awesome. And we'll hopefully be observing in June or July as well. So looking forward to it.
This is Mike Gardner up in Berkeley, California, and I'm a member of the VSO, and we, like you, have a division that does study and try to find exoplanets. So if people are interested in that, they can check out the AVSO as well as the site that Rob, you gave. By the way, an excellent talk. Thank you very much.
Oh, thank you. Yeah, working at the AVSO has been awesome. There's so many great, passionate observers that have taught me a lot, and a lot of them have been giving us input over the last year and a half now on making things more user-friendly. And really, it's the opportunity to work with hundreds, if not thousands, of amateur astronomers to achieve this science, which is really incredible and cool. I've been talking a lot about Exotic to use for data reduction tools. You can use whatever data reduction program you want. So if you're more comfortable with using AIJ, AstroImageJ, you can do it as long as it's in the correct, text format to upload AVSO and makes Dennis Conti happy. That works for us as well.
Yeah, I have another question about, you talked about doing exoplanet hunting using a small telescope. Now, is there a requirement that it should be done from a dark sky, or it can be also done from the urban skies?
And that's what we hope to prove, actually. So we actually have someone that is also in the San Gabriel Valley. I live in Monrovia. There's someone in Glendora, just a town or two over from me, and they're actually able to produce amazing astrophotography. I actually have a 6-inch Celestron with, I forget the brand, digital camera. I'll be testing that out from my own backyard to see if I can do transits as well. We really want to push this to eventually open this up to everyone and anyone, including people who are in the LA area, for example, or any area with bad light pollution. A lot of these planets are transiting around stars that are luckily bright and potentially are available to small telescopes. So even if you're in a non-dark sky location, as long as you collect the photons from the planet, that's all that matters at the end of the day. Also, if your data doesn't look like the best, that's not a big deal because we're also doing a strength in numbers play. So if you get multiple people observing the same transit, you can bin all their data together to make one nice fit to that light curve. And we're actually starting to do this on our website right now. Actually, I pull it up here really quickly. So here's our website. If you Google Exoplanet Watch, you'll find this. And here's a quick plug for the AAVSO. If you're not a member, definitely go check it out. It's a great organization that does typically variable star astronomy. Now they're starting to get into transiting exoplanet observations. But if you go to our results page, you'll see a still being made. You can see all the targets that are currently on the AVSO database that we've also fit ourselves and put into our catalog. And if you go to this target, for example, Kuro 2, here's 3 observations done by amateur astronomers to refine that mid-transit time. So while this observation might not be as high quality as this one, it's important still to get new data that's relatively recent to whittle down the uncertainties on those mid-transit times. What's pretty cool is you can actually see the light curves here too. So that's a really nice low scattered light curve. And here's one done by actually a 6-inch telescope, a little bit more scattered than the one I just showed you, but all 3 are really important to getting more observations on these planets to use large telescope time more efficiently. So just because you don't have a 12-inch, 15-inch observatory doesn't matter. You can still contribute to the science, definitely.
Okay, so the requirement is you just collect photo on that. You're saying that it doesn't have to be a certain amount of time or number of observations, as long as it's defined, the area of the sky is determined by the ExoWatch. But okay,
Yeah,
you have to.
As long as you get the transit, and you can eventually even start to get partial transits. We haven't had a lot of stress testing of those yet, but typically a transit event takes on the order of about 5 hours to observe from beginning to end. That includes out of transit baseline. So as long as you get that and you get a transit looking light curve, that's all that matters at the end of the day.
Very interesting.
Yeah, thanks for the questions. Appreciate it. Any other questions at all?
Has the SETI organization, knowing the location of Earth-like or rocky planets in the Goldilocks zone, tried to listen in specific directions and what's going on there?
Yeah, I think they have. I haven't seen the latest yet because I've been in COVID lockdown like everyone else has, so we haven't had a chance to go to the conferences necessarily. But yeah, I think today we know about 20 to 30 planets in the habitable zone of their host star, and a handful of those are rocky Earth-like planets. Some of the more exciting ones, for example, are the TRAPPIST system that I showed earlier, where you have those 3 rocky Earth-like planets, potentially Earth-like planets, in the habitable zone of their host star. Given that TESS is still observing, I think it's probably only a matter of time until we discover more and more planets in the habitable zone of their host star. And then once James Webb launches and then the next generation of telescopes launch, we'll be able to figure out if life exists on their surface or not, hopefully. Yeah, great question. Thanks.
Thank you. Certainly shake things up to find out somebody's really there.
Okay, do we have any more questions by any chance?
And if you do come up with any of the questions or realize you have more questions about Exoplanet Watch, just Google for our website, and then there should be a link to our email address on there. And hopefully I'll see a bunch of new signups happening on our Slack channel tonight. Also, if you find something isn't user-friendly or not intuitive, please let us know. Now is the time to let us know of ways we can improve the project. And really, there's the opportunity for each of you to contribute with sculpting the project and making it what you want, making it into what you want out of it. We're trying to make a really great community feel by having everyone help each other and, you know, be opening and accepting of everyone and anyone. So really hope I see some more folks signing up from this as well. Thank you so much for having me, everyone. Really appreciate it. And feel free to get in touch via email with me again soon.
Thank you. Thank you. For a great talk.
Very nice.
Okay, that was
Thanks,
a
everyone.
fantastic talk. We really appreciate that. It was a great talk. We've seen, I think this is the second or third one we've seen of exoplanets in our club now, and it's all three of them have been very, very interesting. Okay, so if we don't have any other questions, Spencer, do you want to go on to the chat and see if there's any questions on the chat?
I just checked. I didn't see anything there. But,
Okay.
So just a reminder, if you have not signed up for the door prize drawing, only 13 out of 32 have signed up. So please, I'm reposting the link in the chat right now. So sign up, and I'll give you about another minute to sign up, and they'll close it out, and we can continue with the drawing.
In the meantime, Curtis, can you introduce any of the new members?
Yes. Do we have any new members? We only have 31 this time online. Do we have any new members online tonight? Doesn't sound like it. At least I don't see any. Nobody's raising their hands. So I'm assuming we don't have any new members online. So do we have any other announcements that anybody can think of before we open it up to the door prizes? Alicia, are you online?
Yeah, I'm here.
Okay, good. So when Spencer releases the door prizes, closes the door prizes off, then we can go ahead and have our door prizes.
Okay.
You want to talk about the door prizes tonight, what we have?
Just one quick second. Let me interrupt for a second. So there are 16 people who joined. Now, some of you who joined really early I might have inadvertently wiped your name off when I reinitialized the list, because I made the announcement before I reinitialized the list. So if you joined really at the very beginning of the meeting, go ahead and I'm sorry, if you registered at the beginning of the meeting, go ahead and register again, and I'll remove any duplicates before we have the drawing.
Okay, I'll check that. Okay, I'll do that because I did go pretty early.
Okay, so. I got you. Kurt.
Okay, you got me and Carol. Okay, that's great. Yeah. Mm-hmm. You got Carol too?
Yep. Mm-hmm.
Okay. Okay, whenever you want to close it off, Spencer.
All right.
How many do we have now?
Let me just see. Let me just check here real quick. Now we have 21. Okay. All right. Last call.
I just sent one. I don't know if I was in. I started really early.
Let's
but I just
see.
sent another one.
Okay.
So did I.
All right. Let's see. Okay, I got yours, Daryl. and Tim Thompson.
Yep.
Yeah, I got you, Tim. Okay. All right. I think
we better win something then.
Okay, yeah, we have a pretty high probability of winning something tonight. Okay, Spencer, or go ahead. Alicia, it looks like Spencer has closed it off. Alicia, it's your floor.
Okay. So we have some really nice, we have some really nice door prizes today. We have some Amazon gift cards. We're giving away items from the LAS website. We're giving away LAS hats. some red flashlights, and a laser. And we have more lasers coming on the way.
Don't need any more.
No heads, no
Yeah.
heads.
All right. So are you ready, Spencer?
Just 1 second. I'm downloading the list now.
Okay.
Hang on a second. Sorry about that. Can somebody sing while I do this? Hang on a second. You know, this has gone flawlessly for how many meetings, and then tonight, starting with my computer hiccuping.
It must have caught COVID, Spencer.
A different kind of virus.
Yes.
It's called Windows Update.
Okay, finally got it. Yeah, that too. Okay, now let's get the other spreadsheet going. Hang on a second. All right. Okay, finally.
Since we're talking about exoplanets, for those of you that don't know, on the unistellar applications that we have on our phones, it has an area for exoplanets, and the SETI Foundation automatically sends the information to my phone and asks me if I want to do citizen science. I just push yes, and it sends all the telemetry to the telescope and collects all the data over a period of time, and then I just upload it. It goes back to them, and they send it to NASA and JPL. It's all done.
We always suspected you were talking to aliens, David.
Yes, you're welcome. It's great.
So you don't actually have to do anything at all except sit there and watch your telescope do all the work.
That's correct. Yeah, sorry guys. I know.
I'm not lazy man's astronomy.
Yeah, you're right. I know, but I'm enjoying it.
Okay, I'm sorry. Keep going. I'm almost there.
It's Tim. I don't have the expertise you have. That's the problem. I really don't.
Oh, I see. Okay, hang on. All right.
And just to make one final plug for our project, even if you aren't good at astrophotography, like me, you can still do transit observations. You don't need perfect guiding, perfect focus.
Yeah, this is Greg Thompson, and I'm our outreach coordinator for a scouting program.
Yeah.
There are 15 summer camps around Southern California that all put thousands of youth through the astronomy merit badge each summer. And I'm in contact with most of them. I'm going to be volunteering up at Circle X at Lake Arrowhead this summer, and they actually have a pretty decent observatory.
Awesome.
And power and all that internet. So I'm thinking, man, that would be pretty exciting for the scouts to observe something, data live like that. I've got the camera and we've got the scopes. It's just a matter of hooking up that software. So thanks for the tip. If watch our bulletin, maybe we'll have some youth actually doing it live this summer. That would be super cool.
Yeah, and anyone feel free to join. The best way to keep in touch with us is via our Slack channel. It's just like a messaging app, basically. And it's how we all sort of keep in touch with each other and help each other fix any problems as we move towards launch. So yeah, I'd love to see you out there, Greg. And
I might have to do a dry run on my own before I do it in front of people. But what a great, exciting thing that would be for the scouts to contributed to science right at the forefront. And that's really cool.
And that's why we're doing it, to hopefully help inspire future generations to do this as well.
Okay.
Rob, I think you're probably going to get some response once people in the club start finding out that they can actually do some science and add to that. When that starts trickling out there, you'll probably start seeing some response from our club members, I would think. We got a lot of people who do astrophotography out at our dark site in Lockwood. When they get wind of this, they're going to have a target.
Yeah, and there's always a transiting exoplanet any night you want to observe. So yeah, look forward to it. Sorry, I don't want to interrupt now.
All right, that's okay.
That's okay. There we go.
Are you seeing
Prizes
the
are
spreadsheet?
important.
Are you seeing the spreadsheet now?
Yes.
Yeah.
Okay. All right. So the first one is Javier.
What did
Okay.
Javier win?
Javier won an Amazon gift card.
All right, yay.
Okay. Ah, Daryl.
Hey, what you
Finally.
got? What do you got, Lisa?
You won a 60-inch night, operator.
He won an LAS website item.
Okay, cool.
Okay.
Hey.
All right.
What's that?
Omar.
Omar won an
Oh,
LAS
yay.
hat.
Awesome, guys. Thank you.
All right. Next. Juan.
Juan won a red flashlight.
Woo! Oh, make sure it's not too bright.
All right.
I know I have to use a different brand. I was so mad. I was like, oh, you gotta be.
That was like a red searchlight.
Well, you realize you can pull it in and out to change the focus, right?
Yeah, but it's
It's
Spencer-
bright.
Still
Right.
too bright.
and Rob saw it too. John saw it too. I mean,
Yeah, from right across the field. Okay. Next one. Carol.
Carol.
Hey.
Carol won an Amazon gift card.
hey,
Oh,
She said right here.
wow.
I heard her.
Okay.
My God.
Let's see what happened here.
You deleted somebody wrong.
Yeah. Yeah. Okay.
Amazon gift card.
$25.
$35.
We can hear you.
Open mic, open mic.
Hang on just a second. I forgot to delete Omar. Oh no, this is a different. Wait a minute, did we do Omar already?
No.
Omar already
Oh,
won.
yeah, that's what I thought. He was.
I'll take a second gift.
I forgot to I forgot to
Just
dedupe him.
curious to see if he's
Okay.
winning again.
Jose.
Jose won an LAS website item.
All right, thank you.
Cool.
Okay.
Man, Jose keeps winning.
Yeah, and I still haven't gotten a laser.
All right. How many more do we have?
one day.
3.
Ricardo.
Ricardo won a LAS hat.
Hooray!
That's you?
Boy.
Okay. Edward Smitter.
Won a red flashlight. Wait.
Oh, thank you much.
All right, and the last one's for the laser.
Tim Thompson.
Oh boy.
New laser.
I'll take it. The one I've got's got a bad switch.
Perfect.
All right.
Add to your collection.
Yeah.
So you actually use this one, right, Tim?
I do. It's the green laser.
Yeah, it's the green laser.
And at least the one I have that with the bad switch has the front end of it defocuses, and it's really good when I get the 60-inch or at Mount Wilson anyway, and the 100-inch giving talks. If I defocus it, it makes a nice big green spot that people can see without going blind. So it's great.
You know, it's my red flashlight, Tim.
Hey Tim, have you ever tried pointing it through the eyepiece and seeing?
I have,
and
it's actually a little bit harder to align than you might think, But I've sent a green beam to the moon. I no idea whether the moon people saw it or not. I've done that a few times.
Awesome.
Okay. All right. Well, that's it for the drawings. My apologies for the delay when I was futzing around. But anyways.
It's okay.
That's okay, Spencer. We got through it. And Alicia, thank you for doing the door prizes. And Spencer, thank you for doing the door prizes. So
All right, cool.
do we have any other announcements or any other comments anybody wants to make?
What's upcoming? You might want to tell about upcoming events or anything.
I got a couple.
Yeah, go ahead, Greg.
Okay. Well, as we met on the board, the flyer for our astronomy merit badge program is now being sent out. So I'll be sending that to the board. But just so the club will know, I've got 3 Wednesdays. June 23rd will be online, but July 21st and August 18th are planned for Garvey if it's open and available to us. If not, I'll have to convert those to online. But we're hoping Garvey will be open on Wednesday nights. So there'll be more information on this coming. Obviously, if we're doing either online or in person at Garvey, club members can volunteer to join the Zoom and demo, or come in person out to Garvey and set up their telescope to share with the scouts. So that program is actually going out, and I'll keep the board informed. And we're looking forward to this summer and getting back to Garvey anyway. So that's good.
Yay.
Hey, great. Greg, appreciate that. Okay, any other comments or questions?
All right, a comment from up here.
Yeah.
We are supposed to get snow tonight.
Oh, how exciting.
You guys were squeaking about 37 degrees at the dark side. I still remember the 2008 RTMC, the warmest night, 11 degrees.
Oh.
And after that, it got cold.
Yeah, I remember that, Jack. I remember that.
Hey, Curtis,
Okay.
didn't you go out observing last month?
Well, Joe and I went to Joshua Tree in April, and we had Saturday night was not very good. We just sat there and enjoyed the sky with the binoculars. And then Sunday night, we were looking at Monday night, Monday night. Monday night, we were actually looking through his 12-inch reflector, and with a laser finder on the 12-inch reflector, we were able to find things very, very quickly in the sky. And we were looking at Markarian's chain, and we saw, I remember 7 or 8 galaxies in that field of view. So yeah, we had a good night that night. I was also able to track down that extragalactic star cluster in Lynx. I was able to track that one down on my 6-inch refractor. So that was something I've always wanted to look at. But we had a good time over there at Joshua Tree. Like I said, last weekend we were up at Ford, and we had problems with the cage on the top was not rotating, so we could not observe with Ford, because we would have had to keep our neck in some obscure angle to be able to look through the telescope. So, but anyway, I have a question for Spencer.
Yeah, go ahead.
Spencer, on your shirt, you have a picture. It looks like a tube oscillator from the 30s.
Eccles Jordan flip flop.
What was that?
The Eccles Jordan flip flop.
Wow.
Designed 1919.
Yeah, I kind of recognize something like that on your shirt there.
You guys that old?
Huh?
You guys that old? Wow.
Well, I recognize the tubes on it. Okay.
Hey,
well,
when I took my college electronics class, we were still using tubes. All you digital guys just don't know how exciting electronics can really be.
Well, when I first started to go to college, also, Tim, I took a class at Mount SAC in tubes. The guy who was over there still teaching a tube class. I took the tube class he had.
Yeah, that was my electronics class. We were just learning how to design with tubes, and
Yeah.
and the other students would say, "Why are we fooling around with tubes? Because they're transistors now." But the instructor said, "Yeah, if you learn the fundamentals with tubes, you can apply them to transistors." And he was right.
Yeah, it's pretty close. And one of the main advantages of tubes at that time was the fact that they could put out megawatts of power, and a transistor couldn't do that.
Yeah.
So that was one of the reasons.
You can still use tubes in applications that require radiation hardening, like a gamma ray burst after a nuclear blast. The tubes will survive in the solid home. So there you are.
1287
guys.
forever.
I think we're okay on the meeting, and if there's no other announcements, I will go ahead and adjourn the meeting for tonight.
Thank you.
Okay, no other announcements. Okay, I'm going to go ahead and adjourn the meeting. The meeting is officially adjourned.
All right.
Thank you, guys. Appreciate
Thanks
it.
again, Rob.
Thank you very much, Rob. Very much.
Good night.
Really,